Okay, so let's do that. So for lambda equals 2, we're going to do the same thing. We're going to go up to lambda I minus a, plug in lambda equals 2 for this, and then find the null space, find a basis for its null space. So let's do that. If I plug in 2 for lambda, I'll get 2, 0, 2, negative 1, 0, negative 1, and then negative 1, 0, and negative 1. That's what you get if you plug lambda equals 2 into this matrix. And that's all I've done here. You can check that that's what you get down here. So then you're going to turn it into the associated homogeneous systems augmented matrix by adding the zeros on the right hand side, and then you're going to row reduce it. And again, I'll leave it as an exercise to you guys to show that, but you can row reduce this down to the following. You'll get 1 0 1 0 0 0 0 0 and then 0 0 0 0 again. That's the reduced for echelon form of that matrix. And now what you actually see is there's 2 rows of zeros here, and we actually only had one leading one. So we're going to have 2 parameters. We're going to have a parameter for x2, and we're going to have a parameter for x3. So let's assign parameters. So x2 is equal to s, and x3 is equal to t, let's say, for arbitrary real numbers s and t. Okay, so that's our parameter assignment. Now for x1, there was a leading 1 in that column, so we're going to solve for it and write out the equation. So we get x1 plus x3 is 0, or in other words, x1 is negative x3, which is negative, what was that? x3 was t, right? So it's negative t. All right, so let's write down the general solution. So the general solution, write it in vector form again. We'll get x1, x2, and x3, and we'll write the general solution down. And what will we get? We will have x1 was negative t, x2 is s, and x3 is t. And notice we've got 2 parameters here now. So we can't just factor out an s, and we can't factor out a t here because it's not a common factor to all the coordinates, but we can split it up first and then factor it out. So I'm going to go negative t, 0t, plus 0s, 0. Right? Those 2 vectors certainly add up to this one, but now I can factor out the parameters. So I can say this is t times negative 1, 0, 1, plus s times 0, 1, 0, and that's my general solution. So what you've shown now is that the eigenspace for the eigenvalue 2 is actually the span of these 2 vectors, negative 1, 0, 1, and 0, 1, 0. So now you've got a basis for the eigenspace E2 that has 2 vectors. So you can, and I mean, you could check that they're linearly independent, but it's pretty clear that they are, since this one has a 1 in the second coordinate, and this one has a 0 in the second coordinate, and this one has a 1 in the third coordinate, this one has a 0 in the third coordinate. It's not too hard to show that those 2 vectors are linearly independent. But actually, I mentioned this once as a passing comment in one of the previous sections. I'll just remind you of it. Whenever you're finding a basis for the null space, when you get to this stage, the number of parameters you have, each one of those parameters is going to give you a separate vector for a spanning set for your null space. Really, which is what an eigenspace is. It's the null space of a very specific matrix. These will automatically be linearly independent. So you can check if you want, but you're not obligated to check because I promise you that that will always work. So what is the dimension now of E2? 2, because you've got 2 vectors in a basis. So the dimension of E2 is 2, which is what we were hoping for. So you can say at the end of step 2, if I add up the dimensions of the eigenspace, dimension of E1, which is the eigenspace for the eigenvalue lambda equals 1, plus the dimension of the eigenspace for the eigenvalue 2, they add up to 3, which is what your n was, right? A was a 3 by 3 matrix, so n is equal to 3. So that means this matrix is diagonalizable. So that's great. So we can go ahead and move on to step 3 now. So we can form the invertible matrix P as follows. So just take the eigenvector associated with lambda equals 1, and that was the one we got for our first eigenvector. Back here, where is it? Right here, or here. This was our eigenvector that we wanted to use, -2, 1, and 1. So that's the first column, and then now I'm going to use these two eigenvectors for the second and third columns. So I'll go 1, 0, 1, and 0, 1, 0. So that is the invertible matrix P. All right, so that is the brunt of the work for diagonalization. And I'm just going to add in some comments now. It may be checked that if you were to multiply P inverse A times P, and what would be involved in calculating that? Well, you'd have to find P inverse. How would you do that? Well, here's P, find its inverse. Use the matrix inversion algorithm. It's a 3x3 matrix. It'll take you a few steps. It's not impossible. I'll leave it as an exercise to do that to you if you're interested in verifying the remark I'm about to make. But you could find P inverse, and then you could multiply it by A. That would be a product of a 3x3 matrix and another 3x3 matrix. And the result would now be a 3x3 matrix, which you could multiply with P. And what you're going to get by our previous theory that we've talked about is you're going to get a diagonal matrix D, which is actually, without even working this out, I can tell you exactly what D is going to be now because of the way we formed the eigenvectors to form P. Right? Remember which eigenvalues these eigenvectors corresponded to. Right? The first column corresponded to the eigenvalue lambda equals 1, and the second and third eigenvectors corresponded to the eigenvalue lambda equals 2. So that tells you how you can form your diagonal matrix. Just put those numbers along the main diagonal and zeros elsewhere. And if you don't believe me, you can check this. Work it out carefully. You've got a product of 3x3 matrices, one of which you'd have to find by taking the inverse of P. You can work that product out, and if you do it carefully and don't mess up, you'll get exactly this, I promise. Okay, so that's diagonalization. Whether or not you actually want to find P inverse, that's going to depend on what you want to do with this result. The fact that it would depend on why you set out to diagonalize the matrix D. If you're trying to find powers of A, like maybe you want to compute A to the power of 10, well, then you might want to actually solve this for A. You can work out what A is, and you can apply the original result that we talked about at the very beginning, right? If you wanted to find A to the K for some large K, well, you could find D to the K very easily and then just multiply by P and then multiply by P inverse on the right afterwards. So that's why in this case, you'd actually want to work out what P inverse is. But since all we were asked to do was diagonalize the matrix, it really comes down to finding the matrix P that you would use to do it, and then also noting what the diagonal matrix D would be. That's really what it comes down to. So we can consider ourselves done diagonalizing here. All right, so I want to make a couple more comments. I mentioned about 10 minutes ago that there would be a time where you might recognize partway along this process that it's just not going to work, and that anything else you do after that is just a waste of time. So that's what I want to talk about next.